All right, so our first topic today will be number theory on, um, we will start with introduction, divisibility, modular arithmetic. I think there is another one, the integer representation as well. So we will talk about the integer representation today. Um, so let me start with the motivation. So a lot of applications in computer science, I mentioned a few here, cryptography, hashing, digit error checking, are applications that need foundations in number theory. So because, for example, when you want to secure a message or you want to encrypt a message, so the computations involved in these in cryptographic applications essentially are based on a lot of results from the number theory. So when we talk about number theory, we essentially focus on integers. So let me just put a note here. The focus of number theory is integers. So here, um, right. So let me just put a pen here. Right. So here, integers. Right. So of course, integers are numbers that everybody integers, right? Like the numbers 1, 0, 2, -3, and whatever, right? So all those integers. We're not talking about other numbers essentially. We focus on integers only. Now, in particular, we look at the characteristics of integers. What are the difference, or what is the difference of integers compared to other numbers, for example? And also the operations you could do on integers. So, for example, these are the applications, these are the operations you could do with integers, like addition, obviously, subtraction, multiplication, and division. Well, division may be a question, right? Not easy. Maybe not exactly an operation for integers, but but we could see later. We will focus on this operation later. So another term that people often use for number theory is arithmetic. So the core part of number theory is arithmetic. Essentially, it talks about the operations on integers. Now, let me just put forth a set of notations here. So we will use Z to indicate all integers, set of all integers, so Z. And then set of all positive integers will be Z plus, so we put plus here. And then Z minus will be the set of all negative integers. Now, there is also another set, familiar one, which is the set of natural numbers, where in computer science, we define set of natural numbers to start with 0. So 0, 1, 2, 3, 4, and so on. So not starting from 1. You might understand this. You might have understood this in high school, for example, saying that natural numbers start from 1. But in computer science, the convention is that we start from 0. Essentially, 0 is a natural number, and so is 1, 2, 3, and so on. So therefore, a set of natural numbers is the same as the set of non-negative integers, right? Now, let's start with divisibility and modular arithmetic. So let me ask a few questions. What is the difference between the divisions 18/3 and 16 divided by 5? Can anyone give an opinion? What's the difference? Anybody?
The results are 18 divided by 3 will result to an integer, where 16 divided by 5 will result to a decimal or a floating point number.
Okay, that's a very good point. So in other words, 16 divided by 5 gives you an integer or not?
It doesn't give us an integer, sir.
All right. So that what makes division special, right? Because division, in comparison to addition and subtraction and multiplication, when you perform division on integers, you don't always get integers, right? Yeah, as a result. Now with this, then we could distinguish, right? So, for example, between 18 and 3, there is a relation between them, right? Between 3 and 18 in the context of division. So what do you think is the relation?
18 is a multiple of 3, sir.
Correct. So 18 is a multiple of 3. How about 5 and 16?
16 is not a multiple of 5, sir.
Correct. So this is a like multiple of or divides, right? In this case, 3 divides 18, and well, of course, 5 does not divide 16, right? So that's the key, right? So therefore, one of the first things we learn about integers in the context of number theory is the operation. This is the division operation, right? So division operation where like the regular division does not always give us an integer. So we have to look at this more carefully. Now, in number theory, the relation of like, for example, 3 divides 18 is called divisibility relation. So it's divisibility relation, meaning that we say A divides B if and only if B is a multiple of A, right? Or in other words, there exists an integer C such that B is equal to A times C. Here. So there is an integer C that such that if you multiply this C with A, you get B, right? If that holds, then you will say that A divides B. Yeah. An equivalent definition would be A divides B if and only if A over B, so A is dividing A with B, gives us an integer. So A per B is an element of the set of integers. So if A divides B, then we could write with a notation like this. Sorry, with the bad writing. So here, yeah. So A with and then a vertical bar B, A, a vertical bar, and then B. So this is read A divides B. Now, if you want to say that A does not divide B, then you use the same vertical bar, but then you cross this out, right? So you make a cross. You cross this out, right? With a backslash, right? Now, if A divides B, then we will call A a factor or a divisor of B, and as one of you said earlier, B is a multiple of A, right? So with this we have a clear and formal definition of what it means for a number to be able to divide another number, right? So you say number A divides B, or an integer A divides B if and only if there exists an integer C such that B is equal to A times C, or C times A in this case, right? Now, obviously in this case, C is also a factor or divisor of B, right? And also B is a multiple of C as well. Now, here is an example, a few examples. So let me ask a question. Is 7 divides 13? This would be easy. The answer is?
No, sir.
No, right. So how about 3? Does 3 divide 12?
Yes, sir.
Yes, sir.
Yes, great. Now, the third question. If we have a number N and D, how many positive integers are there that is not greater than N and divisible by D? Can anyone give an answer to this? let's start with some examples, right? So let's say n is say 12, right? And then say d is say 5, right? So what are the integers? So the positive integers that is no greater than n and divisible by d. So essentially, you look at the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? So out of these 12 numbers, 12 integers, which of them is divisible by 5 and which are not?
5 and 10 are divisible by 5, sir.
Correct. So essentially 5 is divisible by 5. And then do we have another answer? Do we have another number?
10, sir.
10, correct. So 10 is also. Is this it? I mean, do we only have 2 here? Do we have more? Is there any other number?
No, sir.
No, right. So only those 2, right? Now, what? So how do you get? So essentially, for this, the answer is 2, right? 2 numbers, 2 integers, right? You know, we asked how many positive integers, right? So how about say n is say 100, yeah, and then d is say 4. How many integers? Let's call this s, right? What do we s here?
25, sir.
Why do you get 25?
Because 100 divided by 4 return 25, and it is an integer, which means that there is 25 numbers that is multiple. Yeah, something like that.
Okay, so essentially what we want to do is essentially we look at this, right? So the numbers. So what will be the smallest possible multiple of 4, right? So you start with 4, right? Which is actually 1 times 4, right? Right. So and then what will be the next number? That will be 8,
8,
right?
sir.
So it's 2 times 4, and the next number will be 12. So 3 times 4, right? And so on. Essentially, you get, like, for example, 96, which is 24 times 4, and of course 100, right? 25 times 4. So if you count them, 1, 2, 3, and so on until 25, you get 25 here, right? Now, what if n is 100, but d is say 9?
You floored, sir.
10, sir.
So the answer is
10, sir.
10, right? How do you get 10?
I mean 11, sir. Sorry, sir. 11.
11. Okay, 11. What? How do you get 11?
100 floor division by 9.
Correct. So, right. So 100 you divide it by 9 and you take the floor. Why is that? Well, because you do the same thing like here, right? Trying out all multiples of 9s and you get on 11 of 1, right? So yes, so that means here the answer is n divided by d, and then you take the floor, right? So this is a floor function. We will define this more formally later, right? Good. So so we understand divisibility. What are the things we could get from divisibility? So what are the properties of divisibility? So let's have a look at these examples. So for example, we know that 13 divides 65 and 13 divides 221. Yeah. 13 times 17 is 221, right? No, 13. Yes, correct. So 13 times 17 is 221. Now, and then from these two, we understand that 13 divides 286. So what do we get here? So why does this hold? Can anyone see the pattern here? So for example, if A divides B, and then also, sorry, let me use C instead of B. A divides C, and you also have B divides C. So what do you get? What about this? This is A, this is C, this is B, this is C. And, well, what is 286? Can you get 286 from 2021 and 65?
Yes, sir. The sum of
Yeah, the
two
sum.
numbers.
Right. So, so sorry, I think I made a mistake here. Right. So let me just A divides B, and then A divides C. Then you get that A divides B plus C. Right. Now, similarly like this, right? Here. Yeah. What is the difference here in this case? If A divides B, then A divides C, and A divides what?
C minus B, sir.
C minus B. Yeah, or B minus C, doesn't matter in this case, right? Similarly, oh, okay, so that's the rule. How about this one? What would be the principle?
A divides the multiple of B, sir.
Correct. So A divides B, then A divides the all multiples of B. Yeah. And here, how about this one? If A divides B and B divides C, then you could conclude that A divides C. And finally here, what will be here, the last one, A divides B, and then A divides C. Now, how about 102? Can anyone guess?
A divides BC, sir.
Is it BC? Is it BC? Anyone? So what will be 102 in relation with 18 and 24? No one can guess? So let's see. So what is 102? 102 is
17 times 6, sir.
7.
17 times 6.
17 times 6. So yes, that is correct. But what we want to say is not that, right? So what we want to say is actually 102 is so 102 minus 24 will be 78, right? So let's see, let me.
Is it 2 times 24 plus 3 times 18, sir?
Yes, so 54 plus 48. Yes, that is correct. Yeah. So here is the key. So that means we could conclude that if A divides B and A divides C, then A divides well, multiples of B plus multiples of C, right? So something like this. So that's the principle, right? So then we get, and essentially here you could also write 6 divides, of course, 3 times 18 plus 2 times 24, right? So this is kind of obvious, right? Because if 6 divides 18, so 6 divides 3 times 18. And then 6 divides 24, and therefore 6 divides 2 times 24. And because 6 divides 3 times 18, and 6 also divides 2 times 24, we get that 6 divides the summation of those two, right? All right. So these are the principles. The proofs are in the textbook. Let me just write one, how to write it. Like, so let me just write the part one, right? So if A divides B, then what? Then A is a multiple of B, right? So, sorry, B is a multiple of A. So that means B is equal to M times A for some M, right? For some integers M. And then if A divides C as well, then C is equal to some N times A for some integers N, right? Now, therefore, if you combine this together, then therefore, if A divides B and A divides C, then of course B plus C is equal to MA plus NA, which is equal to M times, sorry, A times N plus M plus N, which means that, of course, A divides B plus C, right? Because B plus C is a multiple of A here. Yeah. So that's the proof. The rest are similar, right? Okay. Any questions so far? No? Okay, if not, then let me continue. So in the previous theorem, we talk about the numbers that divide another number. So essentially divisibility relations. So where the divisibility relation holds, right? Now, in the next part, we will look at the other cases. The other case, namely that when a number does not divide the other number, right? So for example, what happens if we divide 19 by 5, 12 by 4, and minus 13 by 7? Let's focus on 19 by 5. So what do you get? What happens if we divide 19 by 5? Anybody?
You have a remainder, sir.
We have what?
Remainder.
We have remainder.
A remainder.
So could you elaborate on that? Alexander, what do you mean by remainder?
When we have a remainder, the result will be a decimal number, not an integer.
Okay, so for example, concretely, if we divide 19 by 5, what do you get? What will be the remainder?
4.
4. How do you know it's why is it 4?
The remainder is 4, but the answer is different.
All right, so why is it 4?
Because the closest multiple of 5 to 19 is 15, and then 19 minus 15 is 4.
Okay, so essentially you try this out by looking at the closest multiple of 5, which is 15, right? So yes, so you have the here essentially you get 15 and 4, and then this 15 itself is a multiple of 5, which is 3 times 5, right? Yeah. So that means when you divide 19 by 5, you essentially get two numbers if we want to stick with integers, right? We don't want to go outside integers. So you get two numbers, namely 3 here and 4. Yeah. Okay. How about this? Minus 13 by 7. So what numbers do you get? Anybody? Can anyone get? Can anyone do the same thing here? Similar thing with minus 13? No? What would be the closest multiple of 7 to minus 13?
1, sir.
1. 1 is a multiple of 7?
I mean 1 times 7, which is 7.
So 7 is the closest to minus 13. Is that what you're saying?
To minus 14, we have minus 7 then.
Minus
No.
7. Okay. And then what will be this one?
The remainder will be minus 6, sir.
Minus 6. Okay. Minus 7, minus 6. So minus 7 here because you have this is minus 1 times 7, right? That's what you want to say, right?
Yes, sir.
Okay. Right. So we have a remainder, but the remainder is negative here. Right. Yeah. Can we restrict the remainder so that it is only positive numbers?
We can, sir.
Yeah. So in that case, what do we get for minus 13 divided by 7?
The modulus, sir.
Yes, the remainder. The remainder.
1, sir.
1. Okay, so let me erase this, right? 1. Or let me just do it similar thing here, right? So 1 is the remainder, and what will be the other number?
Minus 2.
Minus 2. Why?
Minus 14 plus 1 is minus 13.
Correct. So minus 14. And from here we get, right, like this is minus 2 times 7, right? So how about this one, 12 by 4? Can you get two numbers?
Yes, sir.
Yes. And what would be the numbers?
3 and 0.
3 and 0. Correct. So now, can we write 19 as a combination of the rest of the numbers, like 3, 5, and 4? How do you write 19? Three times 5 plus 4, correct? Yeah. How about 12? Anyone?
3 times 4 plus 0, sir.
Okay, 4 times 3 plus 0, right? And then what about minus 13 with 7? Right? In the first example, you have minus 1 times 7 plus minus 6, or better, if you restrict this remainder to non-negative, then you get minus 2 times 7 plus 1. All right. Now, the number 3 and 4 for 19 here, and then 4 and 0, as well as, for example, minus 2 and 1 are the important numbers related to division between these numbers, right? So, for example, if you divide 19 by 5, then essentially you have 3 and 4 as the result. So 3 is what we call the quotient, and 4 is what we call the remainder. Similarly, when you divide 12 by 3, then you get 4 as the quotient and 0 as the remainder. And of course, with minus 13 divided by 7, you get minus 2 as the quotient and 1 as the remainder, right? Now, this is captured in this theorem saying that if you have A and D integers, such that, of course, D is not 0, then there is always, and there always exists two unique integers, remember here, unique integers Q and R, such that, first of all, R is not negative and less than D, yeah, and A is equal to D times Q plus R. So you could always get the number Q and R this way if you have A and D, yeah. So Q is called the quotient and R is called the remainder. Remember, the remainder must be between 0 and D, not including D. Yeah. Now, in some notations, we could define actually the Q here is the result of this operation A diff D. So diff is essentially an operation to get the quotient when you divide A by D. And of course, the mod operation, remember the bold face, I use a bold face font here. The mod here means it gives us the remainder. Right? So A mod D is the remainder of the remainder that you get when you divide A with or by D. All right. So every two integers, you always have this. Now, let me ask a question. Does A have to be greater than D?
No, sir.
Sorry?
No, sir.
No. Why? I mean,
Because if
or could you give an example where A is not greater than D?
if we take A is 3 and then D is 5, then we can get A equals to 5 times 0 plus 3. Sir.
Right. So that means A is
5 times 0 plus 3.
0 plus 3. Correct. So the quotient is, what is the
0.
quotient? 0 is the quotient and the remainder is 3. That is correct. Yeah. Good. Now, this always holds for every pair of integers, right? As long as one of them is not 0, right? So as long as D is not 0. Now, let's do this. What will be the quotient and remainder when 111 is divided by 13 and minus 13 divided by 3? Can anyone give an answer? What will be the quotient? Or let me just write it. What will be 111? This is 13 plus 1. Anyone?
8 times 13 plus 7, sir.
8 times 13 plus 7. So 8 times 13 is 104, and then 7 is the remainder, right? Correct. So therefore, the quotient is?
The quotient is 8, sir.
Correct. And then the remainder is 7. Yes. Now, how about this one? Minus 13. 3. What will be the quotient here?
Negative 5, sir.
5. And then? 5 or minus 5?
Negative minus 5, sir.
Minus 5. Okay. And then?
And 2.
2. Correct. So this is the quotient and this is the remainder. Good. Any questions so far? No? Okay. Seems as everyone is still on board. All right. So now, if we understand the mod or the remainder operation, yeah, there is a relationship between divisibility and mod operation, right? So this is the statement, like this is a theorem. So for example, so if we have A and B, two integers where a is not 0, then a divides b if and only if b mod a is 0, right? So this is the thing, this is the test we use in, for example, if you write a program, you want to test whether two numbers, whether one number divides another, then you do this operation, right? The mod operation. Yeah. So a and b, a divides b if and only if b mod a is 0. So for example, well, 3 divides 12, right? Because of course, well, 12 modulo 3 is 0, right? So the remainder of dividing 12 by 3 is 0. Yeah. So how do we show this? To show that this is this theorem holds. Yeah. Yeah. Well, this should be quite easy, right? So for example, so we want to show, so I'll give you a way to prove this, right? So if you want to show, you want to prove this if and only if statement, then we have to prove one direction. So from left to right, and then from right to left, right? So let's start from the left to right. So suppose A divides B. So what do we get here? That means, by definition of divisibility, then we have B is equals to M times A for some M integer, right? Now that means what? That means, of course, that B is M times A plus 0, obviously, right? Yeah. And by division algorithm, yeah, we have that, of course, B mod A is 0, right? Yeah, remember the definition here. Here, the remainder, yeah, is called the result of mod. So now, how about the other direction, the left, right to left? So suppose B mod A is 0. So how do we proceed if you want to show that A divides B? Can anyone give the next step? Anybody? What is the next step? So we want to show that A divides B. We start with B mod A equals to 0.
B equals to KA plus 0.
B is equal to, so then, correct, by definition, by division algorithm, right? Division algorithm, we have that B is equal to K times A plus 0, right? So, and therefore, this means that B is equal to K times A, right? Which means, obviously, yeah, obviously that A divides B. Yeah, this is for some K integer, right? So that's how we prove this statement. So this is very easy. Yeah, good. Now, this established the relationship, a clear relationship between divisibility and modular operations. Now, after we understand divisibility and modular operations, the next step is to use this modular operations. Essentially, we get what we call modular arithmetic. So we could do something with mod here, right? So now, there are cases in which we only care about the remainder. So here is an example, some example of the questions. For example, what time is it? Like 100 hours from now. What time is it? Anyone can guess what time is it? 100 hours from now. Right
Is it
now.
100 modulo 24, sir?
Correct. So 100 modulo 24, and what do you get? You get 100 modulo 24.
4.
4, and then what? What time is it?
Plus the time now.
Right. So that means the time now, say, let's say 2 p.m. Or let me just use the 24. Right. So we know that the time now is 14:00, suppose, right? And then plus, of course, 100 mod 24, right? Which is, of course, 18. Right. Similarly, what day is 10,000 days in the past, right? So you could do this by, of course, the day, today's day, like for example, this is Thursday, and 10,000 mod 7 is what? And then you do the subtraction easily after you get it. So essentially, there are questions in which we only want to know the remainder of an integer division, right? So that means we could do some arithmetic with this, right? So let's start with a definition. Suppose you have A, B, and M here, integers, with a condition that M has to be positive. Yeah, M has to be positive. The M here has to be positive. Then we define A is congruent to B modulo M. Yeah, A is congruent to B modulo M if and only if M divides A minus B. Yeah, M divides A minus B. Now, the integer M here is called the modulus, and this notation here is called congruence. Yeah. So we can ask whether a number is congruent to another number modulo some number, right? So that's it. Now, if A is not congruent to B modulo M, then you write A, well, with that equivalent sign crossed out, right? Now, let me ask a question. What is the difference between this and this? Anybody? Are they the same or are they actually different? Can anyone give an opinion? Nobody? What do you guys think? Okay. What is the relation between, okay, let me put it differently. So if you have this, is this a statement that has either true or false? So that could be evaluated as true or false, or is this a statement talking about an operation getting a number from other numbers?
It has a truth value, sir.
It has a truth value. So this one is sort of a relation, right? So you say this is true or false for A and B, right? Yeah. Now, how about this one? Well, in this one, you do an operation of modulo operation here. So you mod A by M. So you take A modulo M. So you get B. So these two are different in the sense that the first one is sort of a between A and B. It's a relation. And here in this case, A and B, well, you could say this is a relation, but more importantly, you perform an operation. So whereas in the first one here on the left, you don't perform any operation in that particular statement. Yeah. Now, let's try this. Yeah. Now, although we know that they are different, they are related closely, obviously. Now, let's try this. Try to fill in this table. What about the first one here? What will be your answer? Is this yes or no? Is 7 congruent to 12 modulo 5?
It's true, sir.
True.
It's
So
it's not true.
it's not true.
Wait. It is true. It is true.
It is true. Why?
Because wait, sir. I'm actually confused, sir. I'm sorry,
Okay,
sir.
okay, that's okay. So let's have a look at this definition, right? A is congruent to B modulo M if and only if M divides A minus B, right? So A is congruent to B modulo M if and only if M divides A minus B. Now try this. Would it be a yes or no? Oh, sorry. Would it be a yes or no?
It would be a yes, sir.
It would be a yes, right? Because of course
5 divides 7
5
minus 12.
divides, correct. Yeah, that's nice. Okay. How about the next slide? Let's go. Let's fill out the first column here. What about this one? Yes or no?
No, sir.
No. Why?
Because 7 does not divide 3 minus 14.
Right. 7 does not divide 3 minus 14. 3 minus 14 is minus 11. And of course, 7 does not divide minus 11. How about this one? The third one? Yes or no? The answer is
Yes, sir.
yes. So why?
14 divides minus 28.
Right, so minus 5 minus 23, right? So minus 28, yeah. So, and of course, how about this? Yes or no? Is it a no? Can anyone give an answer here? Is it a
It's a
yes or
yes.
no? It's a yes, actually. Yes, good. So this is a yes. Where, yeah, so this is actually a yes, because of course, so yes, because because 3 divides, of course, minus 7 minus 4. And of course here, it's a yes, right? Because of course 6 divides, no, yes, 12 and 21 minus 9. 1 second. 21 minus 9, which is of course 12, right? And of course, finally, this is a no, because 6, should be not divide, right? 6 does not divide 17 minus 4, right? Now, what about the mod? What would be A mod M? What would be 7 mod 5?
2, sir.
2, right? How about 12 mod 5?
2.
2,
Also,
yeah.
sir.
Yeah, good. How about this one? 3 mod 7.
It's a 3, sir.
3, and then 14 mod 7.
0, sir.
0. Yes. Okay. So how about this one? Can you guess what will be the if you fill this out? Okay, let's start the one here on the right. 23 mod 14.
9, sir.
9. How about this one? Is this 9 or not?
Also
Also
9.
9, sir.
Okay, also 9, right? Because it's well, minus 5 times 5, right? No, minus 5 times minus 5 times 1, right? Minus 5 times 1. Yeah, minus 5 times 1 plus 9. No. Minus 5 times. Yeah, minus 5 times. So for how do I write this down? Let me just write it down.
I think it's -1, sir.
Yeah, so
Minus 1.
minus 1 times 14 plus 9, right? Sorry. Why am I getting confused here? So 5 and minus 5 is minus 1 times 14 plus 9. So we get this, right? So yes, the remainder is 9. So how about this one? Again, this one is, I think it should be 2, right? Yeah, because of course minus 4 is minus 2 times 3 plus 2, right? Yeah, so this is also 2. And here, this is 3, and of course here, this is 4, and this is, well, 1, right? So you see the relationship. When here you have a yes, then the 2 columns on the right, they are equal. If this column is a no, then the 2 columns on the right are not equal, right? So this could be formalized as this theorem. So essentially you say that A is congruent to B modulo M if and only if the remainder of dividing A by M is equal to the remainder of dividing B by M. So that is A is congruent to B modulo M if and only if A and B have the same remainder when divided by M, right? Yeah, good. Is there a way to prove this? Obviously, yes, there is. It's a theorem, right? So it has to be possible to prove it. It's right. Let's do one direction, right? So the left to right. So suppose A is congruent to B modulo M. Then, by definition, of course, M divides A minus B, right? That means what? That means M divides A minus B. That means A minus B is equal to K times M for some K integer, right? That means, of course, that means A is B plus Kn. Yeah. And then what's next? What will be the next step? So can we use some of the previous theorem, right? So that let's have a look at the previous theorem. So if A is okay, hold on a second. Let me go through this again. Mm, all right. So we want to say is that you wanna what will be the remainder of A divided by M, right? So that's how we look at this, right? So A obviously is by division algorithm is Q1 times M plus R1, yeah, and then of course B is Q2 times M plus R2, right? Now that means, yeah, because of course, because A minus B is equal to K times M for some K, yeah, you have that, of course, you have that Q1 M plus R1 is equal, sorry, minus Q2M plus R2 is K times M, right? So this is the same as writing it down. You want to say that R1 must be equal to R2. So R1 minus R2 is the same as, of course, Q2M minus Q1M plus Km, which is Q2 minus Q1 plus Km, right? So now with this, of course, it means that M divides R1 minus R2, right? Now, but the key part here is that R1 is between 0 and M, so is R2, right? Now, therefore, if this is the case, yeah, 0 is less than equal to R1 and R2 less than M, then of course R1 minus R2 can only be 0, right? So therefore R1 is equal to R2, which is R1 is A mod M and R2 is B mod M. So that's how we show that, right? So the other direction is it's also straightforward, right? So you could try this at home, right? Any question? No? If not, then let's fill in the table. So I think we have this already. I think this is a yes. This is a no. This is a yes, a yes, a yes, and a no. Right? I think this is the same table, right? Yeah. Now, can we write this? Well, yes, we can write this, right? So for example, here in this case, 7 is equal to 12 plus 12 minus 5, so minus 1 times 5, right? And then, of course, well, this is not possible, right? Yeah. Yeah. We cannot write the 3 as the expression 14 plus k times 7, right? So we cannot do that. So how about this one? This one is just minus 5 is equal to 23 plus, of course, 2 times 14, right? And then, of course, here minus 7 is minus 4 plus minus 1 times 3. And then here 21 is 9 plus 2 times 6, right? This is no. Yeah. Okay. Now, the congruence modular congruence can be so from this table, we understand that there is a relationship between this and this expression, right? So between this expression and this expression, and this is stated in this theorem. So this theorem says that A is congruent to B modulo M if and only if there exists an integer k such that A is equal to B plus Km. Yeah. This is pretty easy, right, to show. So the left to right direction will be, well, if suppose A is congruent to B modulo M, so what will be the next step? Can anyone guide me? You want to show that A is equal to B plus Km. We start with the statement that A is congruent to B modulo M. So what will be the next step?
Then M divides A minus B, sir.
Right, so then M divides A minus B. And then what?
Then A minus B equals to Km for some integer K.
For something. Integer K, right? And then that means, obviously,
A equals to Km plus B.
right, correct. Yeah. Now, so about the other direction. This one is also pretty easy. Suppose A is equal to B plus Km for some integer K, right? Now, what will be the next step? Well, then, obviously,
A minus B equals to Km, sir.
correct, A minus Km. Then, of course, that means M divides A minus B. Then that means A is going to be modulo M. So if you have this congruence, then you could write A into something like this. Similarly, well, B, right? Same thing. Now, with that, that means we have established the relationship or the definition between A and the definition of congruence in terms of the arithmetical expression. Now, if you have A, so now like if you look at this congruent relation, right, the congruence relation, if you take 5 as the modulus, the m here, how many integers are congruent to 7? How many integers are congruent to 7? Anybody? How many? So what are the integers? Give me an example, a few examples of integers congruent to 7. Modulo 5, of course.
Is it 1 and 2, sir?
1 and 2? No. The integers that are congruent to 7 modulo 5. So that means an example will be 2. What else? Besides 2. Let me write 2. What else? Well, 7 itself, right? 7 is obviously congruent to 7 modulo 5, right? Because 7 minus 7 is divisible by 5, right? What about the rest? What else? 2, 7, and are they the only integers congruent to 7? What integers are of the same remainder with 7 when you divide it by 5? So A is congruent to 7 modulo 5. So that means A and 7 have the same remainder when you divide A by 5. Right? You divide them by 5. So you divide 7 by 5, you get the remainder 2. So therefore, well, 2 is also, well, 2 is congruent to 7. Yeah. What else? Besides 2 and 7, what else? Anybody? No one? This should be pretty easy, right? How about 12? Yeah, 12 is also congruent to 7, right? 12 is congruent to 7. Yeah. What else? Anyone?
$17, sir.
17, correct. And
22.
22. Do we have a limit here?
No, sir.
No, right? So we could go on and on, right? Is there any number or integer less than 2 that is congruent to 7? Like what?
-3, perhaps.
Minus 3, correct. Yes. And then minus what? Minus 8, right? And minus, of course, 13, and so on. Right. So the answer is infinite, right? There are infinitely many. Yeah. Now, how about integers that are congruent to 6 modulo 5? Then again, you have 6 here, and then you have 1, obviously, 11, 16, and then 21, 26, and so on. And of course, minus 4, minus 9, minus 14, and so on, right? So you see that you could group the integers with respect to some modulus, you could group the integers into different groups, right? Into different groups. In this case, we call them the congruence classes. Essentially, this is one class, this is another class. Yeah. So the definition is here. So the congruence class of A modulo M, you write it with the square brackets A here with subscript M, is the set of all integers congruent to A modulo M. So now if you look at congruence classes of modulo 3, what are they? For example, let's start with the easiest one, 3. What will be the numbers congruent to 3 modulo 3? The answer is, anyone? Nobody? Hello? Three is congruent to what? Modulo 3. Give an example for this one. Anybody?
For 5 star, let's say.
5? Are you talking about 5 here? Is 5 congruent to 3 modulo 3? Is it correct? Is this
Is it any multiple of 3, sir?
correct? So it's multiple of 3. So it's not 5 or 6, 9, 12, and so on. Of course, 0 and minus 3 and minus 6 and so on. Right? So this is 1, right? Let's call it the congruence class of 0, right? We still have some integers not included here, right? So for example, let's start with 1. What integers will be in the same class as 1, modulo 3?
4, 7, 10.
Correct. Right, 4, 7, 10, and so on. Right? This is minus 2, minus 5, and so on. Yeah, good. So that means this is called, this set here is called the congruence class of 1. Of course, this is the same as this, right? Same as, for example, 6. Now this one is the same as, of course, minus 2 and 4 and so on. And of course, the other is this one, right? And minus 1, minus 4. Yeah. And this is the congruence classes 2. Yeah. Which is same as 5, for example. Yeah. Let me ask a question. Is this true or false? Is this true or false?
True, sir.
Is this true? Are you sure?
No, sir. False. False.
Right. So this is false, right? Why? Well, because 11 is not congruent to 54 modulo 5. Yeah. So let's keep that in mind. All right. What is true? What is true is probably something like 11 and of course, for example, 51. They are the same class. Yeah. This is true. Yeah, good. Yeah. Now, With modular congruence, we could perform addition and multiplication. For example, if A is congruent to B modulo M and C is congruent to D modulo M, then it also holds that A plus C, so when you add A plus C, is congruent to B plus D. Yeah. And of course, A times C is congruent to D, B times D, right? So the first one is pretty easy to show, right? So if A is congruent to B modulo M, that means A is equal to B plus Km, K1 times M. And then if C is congruent to D modulo M, then that means C is equal to D plus K2M, right? Now, in this case, we will have that A plus C is, of course, B plus K1M plus D plus K2M, which is equal to B plus D plus K1 plus K2M. So therefore, by our theorem earlier, we would say that we will conclude that they are congruent, right? A plus C and B plus D modulo M, right? Now, the multiplication is also similar, yeah? You should try proving it, right? Now, let's give an example of the previous theorem. So, suppose you know that an example would be, for example, suppose you know that 7 is congruent to 3 modulo 4, yeah, and then say you have minus 2 is congruent to, say, 6 modulo 4, right? So then from here you could conclude that 7 plus minus 2 is congruent to 3 plus 6, which is congruent to 9, yeah, 4, yeah, okay, and so on, yeah. For example, also from here, you know that 7 times minus 2 will be congruent to 3 times 6 modulo 4, yeah. So this is minus 14, this is 18, which is 2, right? Now, but how about this? Now that's the other way around, right? So we know that A is congruent to B modulo M, and C is congruent to D modulo M. Then you say that A times C is equal to B times D modulo M. Now, but how about this one? Yeah. Let me put a statement first, right? If A is congruent to B modulo M, then obviously AC is congruent to BC modulo M, right? Yeah. Why? Because C is congruent to C modulo M, so we could apply the previous theorem. Now, how about the other way around? This is left to right. How about the right to left direction? The answer is yes or no? No one? Okay. So the answer is no, right? The answer is no because, for example, here is an example. 2 times 4 is congruent to 5 times 4, modulo 6. But 2 is not congruent to 5 modulo 6. So essentially, you cannot go from the multiplication into something simpler by crossing out crossing out the multiples, right? Crossing out the factors. You cannot do that, or you cannot always do that. There are cases where you can do that, but in general you cannot do that. Yeah, in general you cannot do that. Another similar example is when you want to use the other congruence as a power of the first congruence. So if A is congruent to B modulo M and C is congruent to D modulo M, does it mean that A to the power of C is congruent to B to the power of D modulo M? Well, the answer is no, right? There's an example there. 3 is congruent to 8 modulo 5 and 6 congruent to 1 modulo 5. But 3 times 3 to the power of 6, which is 729, is not congruent to 8 modulo 5, right? Because it's congruent to 9 modulo 5 actually. Yeah. So here's an example where this doesn't hold, right? There are cases we will find that we will encounter these cases later on when we talk about relatively prime numbers, and we will be able to get cases in which this holds, right? But generally this does not hold. Yeah. All right. So now let's finish up the modular arithmetic with this theorem. This theorem allows us to perform mod operations, like to simplify the mod operations. So for example, if you have a summation of two numbers, you perform mod operations, then essentially you could do that by performing mod operations on the first number and then mod operations on the second number, and then sum both of them together, and then the result is from the result you compute the mod again, right? So you mod A, you mod B, you sum it, and then you perform mod again, modulo operation again. Similarly, if it's a multiplication A times B, right? So you perform A mod M and then B mod M, and then you multiply them together, and then the result is modded again, right? Yeah. So I'll skip the proof. I mean, you could find it in the book, but and it will be instructive to read out. Let's just use this as an example for this, right? So how do you calculate this? Using the theorems, previous theorems. Can anyone help me? Anybody? How do we start this, right? So let's start with this mod, right? So 19/3 mod 31 is, of course, yeah, the same as 19 to the power times 19 times 19 mod 31, right? Which is what? Well, what about 19 times 19? Anybody?
19 mod 31 times 19 mod 31, sir.
Yes. So well, 19 9. So you could write it down that way, right? So let's just write it down, right? Or let me put it simpler in a simpler way. Mod 31 times 19 mod 31, and then you perform a mod 31 again, right? This is the same as, what is 19 times 19? 361, yeah. I think 361, right? 19 times 19. What is 19 times 19?
361, sir.
361 mod 31. Yeah. Times what is 19 times 19 mod 31 is 19, right? And then mod 31. And this gives us what is 361 mod 31? Anybody? What is 361 mod 31? Can anyone give an answer? Give me an answer for this.
20, sir.
What is it?
Is it 20, sir?
20. Right. Why is it 20? Well, 31 times 11, right? Yeah. 20 or 30? 31 times 11 is 341 also. So therefore, 361 is 31 times 11 plus 20. So yes, it is 20. So 20 times 19 mod 31, which is, of course, this gives us 380 mod 31, which is this is what, right? So 31 times 12, this gives us 62 and 31, so 372. So that means 380 is equal to 31 times 12 plus 8. Yeah. So yes. So therefore, that means this is 8. Yeah. Now, as a result, 19 power of 3 mod 31 power of 4 mod 23 is, of course, 8 times 8 to the power of 4 mod 23. Yeah, which is, of course, here 8 to the power of 2 mod 23 times 8 to the power of 2 mod 23. Yeah, and then mod 23. Yeah, which is what, 64 mod 23 is so 64 is 23 plus 6 plus 18, right? Sorry, 21. 23 times 2. Yeah. Yeah. So that means you have 18 here times 18 mod 23. Yeah, which is, of course, 324 mod 23, which gives you, what do you think? This gives us what? Which gives us yeah, so 2, right? So 360 23 times 15 is 5. Okay, so it's bigger, right? So 23 times 23 times 14 is 292, and then 23, so it gives us 2, 2, 3, 2. Yes, so it's 2. So the result is 2. Yeah. So The lesson here is that instead of like you perform the power here directly, you could split up the operation so that you could do a simple operations, right, with more. Yeah. All right. Any questions so far? No. Okay. If there's no questions, let's take a break for 5 minutes. I think we could continue with this like in the next part of the topic, right? Okay, so let's stop here first and let's take a break.